Hi, it's Mr. Srikanth here, and in this video we're going to look at how to sketch cubic and reciprocal graphs. Now, reciprocal graphs are fairly straightforward, and the key point alone should be enough for you to be able to sketch those. So you won't find any examples on that. What you will need to do sometimes with reciprocal graphs is to apply what you know about transforming graphs and translating them or stretching them in order to draw the graph that you've been asked. But we'll focus our attention in this video really on the cubic graphs. As usual, we'll start with the key points, and the key points on this particular topic are actually quite long and they go over the next 2 pages. Now, this first key point about cubic graphs and the shape of cubic graphs, I think is actually quite misleading. And so I'm going to spend a little bit of time talking about this on the first page here. So first of all, you can see that they've shown you a graph where the value of a, so the coefficient of the cubic term, is positive, and they're saying that if that's the case, you'll get this shape. Whereas if a is negative, you'll get this shape. Now, that's absolutely fine. I'm okay with that. There are some exceptions to cubic graphs where they don't quite look like this. But to be honest, I would ignore the exceptions and just consider these 2 shapes. It is possible to have a shape like this one or like this one as a cubic, as they've shown you. They've said that the graph y equals x cubed looks like this. That's completely right. And that y equals negative x cubed looks like this. It's also true. But you ought to really consider various other shapes if they're going to consider those two shapes as special cases. For example, it's also possible to have a cubic graph that looks like this. And you might notice with that cubic graph that there are no stationary points. On the other 4 that they show you, you can see stationary points here. This is a turning point. The graph turns. Here's another turning point where the graph turns. A third one, a fourth one. So those are on the first 2. Here we don't have a turning point, but we do have a stationary point. The gradient is 0. And here as well, the gradient is 0. You can see it's flat if I draw the tangent. Here, this is a cubic graph. This could be the graph, for example, of y equals x cubed add 6x. And that has no turning points and no stationary points. So it's important to realise that a cubic graph doesn't have to have a stationary point. So that's the first thing I wanted to mention. Also, if I get rid of this, the simpler way to probably think about this, the second 2 graphs here, is to effectively say that these 2 points where the graph turns are all at one point. So the graph is microscopically at this point turning twice. Obviously it doesn't actually do that. It would be exactly the same value, 0, 0 and 0, 3 roots all at the same place. But you can imagine that if it turned and then turned again, then it would start to go back up again. Okay, and similarly here. And then finally I want to talk about these values here, a equals 1 and a equals negative 1. Personally, I think this isn't really appropriate because the graph y equals a quarter x cubed would look exactly the same as this one. But obviously here a is a quarter. The graph y equals 2x cubed would also look like this one. It would be stretched, but it would look exactly the same in terms of its shape. So for me, the issue here isn't about a being 1, it's a different thing. It's about the fact that it has all 3 roots at the same place. And in fact, if you want to take that a step further, you could also say, if I just rub this out again, that the graph of y equals 7x cubed add 12 would look very similar to this graph here, apart from it would be more like this, where this point is 12. It would be a translation of the graph y equals 7x cubed. So be careful about these claims. I'm not sure that I agree with them. So that's the first key point, and I've gone through a bit of detail there. Second key point on reciprocal graphs, and reciprocal graphs are relatively straightforward. You should be familiar with them already. If A is positive, then you get this first shape. If A is negative, you get this second shape. And the key point, I suppose, is that x can't be 0, because if it was, then you'd be dividing by 0, which isn't possible. And y also can't be 0, because there's no value of x that you can divide by, so that your answer is 0. Doesn't matter what value of a you have there. Okay, on to the rest of the key points. So the first three really are about the same thing. So if you substitute x equals 0 into a function, then you'll find the y-intercept, so the point where it intersects the y-axis. If you substitute y equals 0, then you'll find the x-intercepts. And when you're sketching a graph, it's important to label the intersects with each axis every time. So these go together. If you have asymptotes, and you'll see from the next bullet point that asymptotes usually occur, well, you always get asymptotes in reciprocal graphs. There are other graphs where you have asymptotes, but I don't think you're likely to meet those in A-levels, so you don't need to worry about those. Asymptotes are lines which the graph gets closer to, but within a particular region of the graph. So an example on the reciprocal graph that we looked at a moment ago, if I just do the positive part, so there's the graph of y equals 1 over x. You can see that it's getting closer and closer to the x-axis here, but it will never touch it as you get closer to it. It will just keep getting closer and closer. It won't actually touch it there. So that's an asymptote. And normally, if it's not one of the axes, you would normally mark the asymptotes on with a dotted line to show that it's an asymptote. If you're sketching a graph, it would be expected that you would show any asymptotes with a dotted line. Okay, if you've got a turning point on the graph, then the gradient is 0. That's similar to the points where I drew the red lines a moment ago on the 4 cubic graphs on the previous page. And if the graph is if the gradient of the curve is 0, then if you draw a tangent, then the tangent must be horizontal. And then it talks about double roots, or I sometimes call those repeated roots. If you have a repeated root, then it will be a turning point of a function if it's cubic, and you'll get that when you have a factorized form in which you can factorize with an index as well. So that's what shows you that 3 would be a repeated root in that graph. So we'll go on to that. We'll see that a bit more in the examples in example 2, but let's move on to example 1 first. So we're being asked to sketch the graph of y equals x subtract 3, x subtract 1, x add 2. Notice that they've given you this in factorized form, so this is reasonably straightforward. They've helped us out here by having it in factorized form. So the first thing I'm going to do is find the x-intercepts. And the x-intercept is when y equals 0. And if y equals 0, that means x subtract 3, x subtract 1, x add 2 equals 0. Which means one of those 3 brackets must be 0, because you've got 3 things multiplied together and the answer is 0. The only way that's possible is if one of them was 0. So you've got x subtract 3 equals 0, or x subtract 1 equals 0, or x add 2 equals 0. So if I rearrange these to make x the subject on each one, then I get x equals 3, x equals 1, or x equals negative 2. So there are 3 different x-intercepts at those 3 values. Okay, we also need to find y-intercept, and that will be when x is 0. And when x is 0, you get y equal to 0 subtract 3, 0 subtract 1, 0 add 2. which is negative 3 times negative 1 times positive 2, which is 6. And also, if you imagine expanding these brackets, then this x would be multiplied by this x, would be multiplied by this x, so you would get positive 1x cubed. And positive 1x cubed means that the shape of the graph will be something like this. Actually, I'm not quite happy with that, because this should be getting steeper at each end, so it should be more like that. Okay, so what else? We know that it's going to cross the x-axis at negative 2, positive 1, and positive 3. So that means the y-axis must be somewhere around here, maybe a bit further to the left. And the x-axis is obviously where I've drawn those 3 values. And then the y-intercept is 6. And of course I need to label my axes. And so there's my sketch complete. It's very important that you don't try and plot a graph when you're being asked to sketch. That takes far too long and misses the key elements, the key points of the skill of sketching. Sketching is about being able to very quickly draw the shape of the graph and the key values along the graph. A little hint for you, you will have noticed that I drew the graph first and then put the axes on. I often find it's easier to do that so that your axes are in the right place. Okay, on to example 2. So this time you can see in the question that there's a repeated root, and that repeated root will be associated with this bracket. So we'll make sure we focus on that when we need to. And that's going to be right at the start, because we're going to first start off with finding the x-intercepts, which is when y equals 0, which means that this is all 0, and so that means x add 2 squared equals 0, or x subtract 1 equals 0. For this first one to be 0, it's if I square root both sides, I get x add 2 equals 0, subtract 2 from both sides, and x is negative 2. For the other one, I can add 1 to both sides, and we get x is 1. So there are our 2 roots, and remember that this one is a repeated root. That's quite important. So it's another positive cubic, so it's still going to have this shape. And this time we need to think a bit more carefully about the intersects. I've just realised I haven't done the y-intercept, so let's just do that. So we get a y-intercept when x is 0, and x is 0 would imply that we have y is 0 add 2 squared multiplied by 0 subtract 1, which is 2 squared times negative 1, which is negative 4. Okay, now if I pop my x-axis in, so let me do that. If I pop it in like this, then you can see that this would give me 3 roots, or 3 x-intercepts at 3 different places, and that can't be right. So that x-axis can't be in the correct place. So let's try somewhere else. If I pop it down here, oops. Pop it down here, then I have got 2 roots this time, here and here, negative 2 and 1, But this root here, this is the one that was repeated, and the repeated root is the one where it touches the axis. You can imagine that at this point, it's the point where you have two roots at the same place, and that's why it touches the axis. So this isn't right either, because this would be when 1 was the repeated root, but we know that -2 is the repeated root. So this is also not right. So we'll try one final place for our x-axis, and that's going to be here. And that will give us an x-intercept of -2, which is repeated, and an x-intercept of 1, which is not repeated, which matches with the working out that we've done. And then we also need a y-intercept, which means we need a y-axis. And we know that it needs to pass through -6. We know that it's going to be nearer to the second root, so it's going to be something like this. And this value here would be -6. Sorry, -4. And don't forget to label the axis. And so there we have the second example completed. Okay. So you should now be able to attempt all the questions on cubic graphs, and I'm hoping that what we said in the key points, along with what you've remembered from GCSE, will be enough to help you with the reciprocal ones. Okay, best of luck, and I'll see you on the next video.